Hello, welcome to my numerical ship and offshore hydrodynamics. So, today we are going to discuss the following things, like we are going to continue the frequency domain panel method, and today we are going to discuss that how I can change the boundary value problem, the general boundary value problem we have discussed in the last class. Today for attack this problem particularly using this discretization technique that we have discussed in the last class, that phi is divided into 3 parts, phi I plus phi d plus summation I equal to 1 to 6. Then, so all these things taking all everything together, how to solve this, that we are going to discuss, and how the boundary value problem changes because of this, that also we are going to discuss. And then we are going to discuss something called the source panel method. Normally, to remember the last class, not last class, the previous classes we have discussed the source dipole method. However, the classical softwares like WAMIT and other thing, they prefer to use source panel method. So, therefore, we are going to discuss on that also. So, this is the keywords that you are going to use to get this lecture. Okay. So, now let us jump into this equation. Now, here you can see that phi that we discuss, the summation of that phi I plus phi d and then j equal to 1 to 6 phi j. Now, here the interesting part is I am going to do this for in complex domain. So, of course, e to the power I omega t is there. So, there is nothing new on this, but here you can see that I multiply xi 0 in front of phi I plus phi d and I multiply xi j in front of the phi j. So, then it is very normal questions like why these things comes here, because if you remember in my last class that what we discussed over there as follows. So, we discussed that our phi, the total phi is equal to that we discuss it is phi I, then we discuss as phi d, and then it is summation some j is equal to 1 to 6 into phi j. So, that is what we have discussed in the last class. So, however, if we come back here, now I can see that it is there of course, but with this xi 0 and xi j is actually we are multiplying, right. So, what is the need for that? So, first let us understand these things. Okay. Now, here now just in sake of convenience, let us put some number to I and d also. So, normally what I do is we can write phi equal to, now instead of phi I we call as phi 7, okay. And instead of phi d we call as phi 0, and then I can add some j is equal to 1 to 6 into phi j, okay. Or sometimes we can call this as 0, this as 7, does not matter. So, finally, that I can write in summation form phi equal to some j equal to 0 to 7 into some phi j. So, in that way actually this is how I can write in coding. So, instead of I we are writing phi 7, instead of d we can writing phi 0, but that is not the issue. The issue is that why I am multiplying this phi with this phi I plus phi d. Why I multiply this is something called xi 0, and why I am multiplying this j equal to 1 to 6 in phi j some xi j. So, the question is this, right. Now, let us try to answer this question first. Now, what we do now, if you look at this physical phenomena, what is happening? Now, I have a ship over here and then this incident wave potential actually hitting this object. and because of this wave hit this ship, then we have some pressure variation along the hull, right. If you integrate the pressure, you can get a force of course, and the name of the force is exciting force. And normally we define this as F E x. Now, if you know that this F E x, this exciting force is summation of the fluid calculus force we call is F k plus the diffraction force we call F d. Now, it is similar to, if you remember in my previous class, it is similar to that picture where it is, this is still, it is not moving, however, the wave is hitting to this object, right. Now, what is happening when this exciting force actually we apply over the ship, then ship start oscillating. Now, when ship start oscillating, we can have different set of waves. What is that? Now, assume that initially this ship is very much statically stable, weight is balanced by the buoyancy and everything is fine. Suddenly, this the ship hits this the wave hits the ship and then the ship start oscillating, right. So, actually this force, why is called the exciting force, because this excites the ship to oscillate. Now, the moment the ship start oscillating, then again we have some different wave field altogether, and these waves we can call as a radiated wave, and this problem we call the radiation problem. Right. So, now let us see the picture. The picture is that ship is very much stable here with there is no waves in and then suddenly the waves hits. So, that excites the ship and then ship start oscillating, and before ship start, because of the ship start oscillating, then we got some radiated wave, and this is called the radiation problem. Now, because of this phenomena that ship is start oscillating, and this is the picture that we refer for when the body this start oscillating in calm water, right. This is the second picture if you remember, and if you add these two picture you will get the original phenomena. So, we are actually this phenomena is splitted into two components, right. And because actually this happens, this oscillates, because of this oscillates, what is happening, again we have some pressure field along this body, and then if you integrate the pressure field, we will get the radiation force. Now, what is the connection between these two? The connection is this, then that this exciting force excite the body, and because of this excitation the ship start oscillating, and because the ship start oscillating we can have some force. Now, the question is what would be the amplitude of that force, right, because this is unknown to me, but what is known to me, I know what is the wave height that actually hitting the body, right. Now, you know that you can, this is my input, that eta equal to some amplitude eta a into cos let us say in real line cos k x minus omega t, if this is hitting, and then we know that phi I, the expression is also, it is eta a g by omega, then in case of a deep water it is where k z into let us say sin k x minus omega t. So, I know this is known to me, right. So, I know that what is the amplitude is hitting this structure, but I really do not know, because now this the radiation, if I try to write this the potential for the radiation potential, this must be some amplitude, let us call it eta r, let us call it eta r, into a similar manner it should be some e to the power k z into either sin or cos k x minus omega t, definitely it is sin, because this phi r also has to satisfy the linear free surface boundary condition. So, if the eta equal to cos k x minus omega, definitely phi should be sin, whatever. So, let us leave that part. Question is, how do I know this amplitude this, right. Now, here is the trick. We use the property of the linearity. It is a very nice property. In fact, from the class 9 we are doing this. Maybe you can maybe before that I do not remember right now, but the day you started the unitary method, we are actually into the linearity. Now, what you say is very simple. It says that let us say that let us take one apple, if it is cost let us say rupees 20, let us say, then in 200 rupees, in rupees 200, I know how many apple you could buy. So, you know that so it is very easy for you, see, it is very simple, because I know that price for one apple. So, it is simply 200 divided by 20. So, this is my answer. So, that means this unitary method teach you, if everything is under the linearity and if you know the cost for unit, then you can find out the total thing that you are spending, right. So, this teach you that the total cost, so under the linearity it teach you this 200 is equivalent to some amplitude eta multiplied by the 20. That means, I know the price for a unit apple, and then I multiply by the, in that case the number of apple, in our case it is the basically the amplitude, that mod, the mod. If you, so the underlying principle of the linearity is as follows, that if you know the thing for the unit amplitude, and if you multiply this unit amplitude with the modulus, then definitely you are going to get the total force. So, this is the idea. Okay. So, see you understand, and it is only possible in the approximation of the linearity, because linearity gives you a nice property, right, and it is called the this is the ratio and proportion. So, it means that if one this cost 20, so definitely this much, so it is 10, this will definitely cost you 200. So, this by this should be equal to this by this. So, this is what we learn unitary method. So, this same logic actually applying here also. So, let us see how we are applying this principle here. So, again let us go back to the slide. Now, if you look at this slide here, now I understand that if you look at this part, this is, now I understand this psi I plus psi d is nothing but the velocity potential for unit amplitude wave. Okay. So, let's so here, so now I understand in that slide this psi I plus psi d is nothing but velocity potential for unit amplitude wave. So, if it is so, so then if you multiply the wave amplitude xi 0, so definitely with this same linearity analogy, I can say that this is nothing but the the force I am getting is basically the velocity potential for our problem. Similarly, if we look at this the right hand side, now here I have the psi j, right. So, now this psi j is nothing but, now this psi j is nothing but the velocity potential for unit amplitude motion. You know that this for radiation probably in still water, this body has to oscillate. Now, that magnitude of this oscillation is 1, then it is psi j. Now, if you multiply this psi j, as I said, the similarly that remember this 20 multiplied by some xi or eta, this equals to 200. So, therefore, this xi j must be multiplied by the amplitude to get the total velocity potential. So, right. So, I am writing here that, so therefore, I can write my phi I is nothing but xi 0 into psi 0, where psi 0 is the velocity potential for unit amplitude wave. Similarly, my phi d is nothing but xi 0 into psi d, right, where the psi d is the velocity potential for the unit, I mean diffracted potential for the unit amplitude wave. And similarly, I can write my radiation potential phi r in jth mode is equals to that xi j into psi j, where psi j is nothing but the radiation potential for unit amplitude motion. Okay. So, with this understanding, let us go back to this slide. Okay. So, now you can see that now this equation 7 is absolutely clear to you, right. It is nothing but the psi, I mean xi 0 into psi I plus psi d and xi is equal to psi j. Now, here what I am going to do is, as I said in the last class, that each of this psi should satisfy the Laplace equation. So, phi satisfy the Laplace equation. So, definitely this xi j into psi j also satisfy the Laplace equation. Now, since xi j is not equal to 0, the other part should be 0. So, therefore, del square psi j must be equal to 0, right, and that is my governing equation. Now, if I know my governing equation, then you can see the equation number 9, which is nothing but the free surface, I mean combination of kinematic free surface condition or dynamic free surface condition, right. So, how it is coming? Now, let us see that how this second equation has come. This is also very easy. Now, here you can write that you know that in time domain it is phi t t plus g into phi z equal to 0, that is in the time domain case. And so, therefore, if you take phi equal to some phi into e to the power I omega t. Now, if you differentiate this 2 times, so phi t t is nothing but minus omega square into phi into e to the power I omega t, and of course, that phi z is nothing but phi into e to the power I omega t. Now, if you substitute over here, what you get is minus omega square into phi, right, plus g into phi z equal to 0, and then it is nothing but phi minus g by omega square into phi z equal to 0. right. So, this is the alternative expression for phi. So, you can see it is here. Okay. Now, I did here the opposite, it is I just divided g, right, this does not matter. And then we need to again understand what is the third equation, which is I omega n. I mean, why it is this let us we need to understand that also. I mean that equation number 10 for j equal to 1 2 3, for j equal to 4 5 6 the boundary condition. Now, here okay, so in this slide actually we did the indexing is the opposite, does not matter. Okay. Like, but let us see that where the indexing here is, here we can we use that phi I is equal to, we can call this as a phi 0, and then the phi d we call as, let us say, phi 7. Okay. So, let us take this, okay. And of course, the radiation potential definitely is j equal to j is equal to 1 to 6 into phi j. So, let us go with this notation, fine. Now, if you remember that from j equal to 1 to 6 is the boundary condition for radiation problem. Okay. And then from j is equal to 7, this is the boundary condition for the diffraction problem. Okay. Now, let us try to understand what is the condition for the radiation problem. Okay. Now, if you remember, the radiation problem is nothing but there is a calm water and then the body is oscillating, and then you can have some radiated wave and you have a pressure field. If you integrate it, you will get the radiation force. Now, here if you remember, I said that psi represent for the velocity psi r, or I can just if I make index j. So, radiation potential for the jth mode is nothing but I oscillate the body in unit amplitude motion. So, I am giving here the oscillation of this body. So, I oscillate this with unit amplitude of the motion. So, definitely my oscillation, this x is nothing but 1 into e to the power I omega t, right. So, therefore, my velocity x dot should be I omega into e to the power I omega t, right, fine. So, now if you remember, my radiation condition is nothing but, that is del phi del n into the jth mode is equals to nothing but v dot n into jth mode, right. Now, this del phi del n is nothing but grad phi dot n into jth mode should be is equal to v dot n into jth mode. So, this is quite simple that we understand this, right. So, therefore, my velocity, I mean that body boundary condition from the left hand side, it is nothing but my del psi del n, right, that is in the jth mode, of course, that should be equal. So, now what is my V n? It is nothing but V dot n. Now, I just find out my V equal to x dot is equal to I omega. So, therefore, I replace this equal to I into omega into n, whether it is not omega n. So, just careful, it is I into omega into n, or you can say n j or the j direction, right, fine. And so, it is happened for j is equal to 1, 2 and 3, right. So, then that means if is j equal to 1, it is nothing but your n x. If it is for j is equal to 1, for j is equal to 2, it is n y, and j is equal to 3, it is n z. Fine. So, similarly, I know that other part also, psi n j, it is definitely we can call r cross n, or here it in slide is called x cross n, does not matter, and it should be j minus 3. Now, we discussed already what is this, because how I get it? It is also very easy. It is if I take I j into k, and then let us call this r. So, you have 3 component r x, r y, r z, and then you have component n x, n y, n z, and if you do that, then you have some ith component, then you have some jth component, and you have some kth component. So, here for del psi del n, now if it is del equal to 4, should be v is I omega, right, multiply by the first component of this. So, definitely it is n. So, j equal to 4 and then minus 3. So, it is nothing but I omega, it is the n, the first component of this the matrix, the ith component. So, that is why I write this as that is why you can in common you can write del psi del n at jth mode should be I omega into r cross n into the not it's r cross n into j minus 3, right. So, this is all about of the radiation potential. Now, only thing is left what happened for the diffraction problem. Now, in diffraction problem, if you remember that what I said is that this the body is fixed and then wave is hitting over here, but body does not move. If the body does not move, then v dot n that should be equal to 0, and then the exciting force as I know is the combination of the phi I plus phi d. So, therefore, the boundary condition become del del n into phi I plus phi d, that should be equal to 0. So, therefore, del phi d by del n should be equal to minus of del phi I by del n. Now, if you remember this I notation this as phi 0 and this I noted as phi 7. So, then I can write del phi del n in 7th mode should be equal to minus of del phi del n in the 0th mode, right. So, let us go back here and you can see that this is the boundary condition for our problem. So, now we understand these boundary conditions now, and then from the next class we are going to discuss about the source panel method. Okay. So, till this point, thank you.